For nearly 100 years, one fact about the universe has been considered settled. Space itself is stretching, galaxies are drifting apart, the cosmos is expanding. But the exact speed of that expansion has become the most stubborn disagreement in modern physics, and the two most advanced telescopes ever built have just made the disagreement worse. In December of 2024, an astrophysicist named Adam Riess at Johns Hopkins University, who shares a Nobel Prize for discovering that the universe's expansion is accelerating, published the most thorough study of cosmic distances ever attempted. 2 full years of data from the James Webb Space Telescope, 3 independent measuring techniques, every method landed on the same answer. And that answer contradicts the prediction made by our best theoretical model of the universe by a margin that can no longer be blamed on faulty equipment. The wording Riess used was careful and deliberate. The gap between what we measure and what our model predicts, he said, suggests that our understanding of the universe may be incomplete, not slightly off, not in need of minor adjustment, incomplete. That is a striking statement from a man whose career helped define the very field now being questioned. To understand why this matters, you need to understand what is actually being measured. The number at the center of the dispute is called the Hubble constant. It describes how quickly the universe is expanding, specifically how much faster a galaxy appears to recede from us for every additional 3.26 million light-years of distance. The further a galaxy sits from Earth, the faster it drifts away. The Hubble constant is the ratio that ties those two quantities together. Edwin Hubble first calculated this ratio in 1929. His original figure was so high it implied that the universe was younger than Earth itself, which was obviously impossible. For the next several decades, astronomers split into opposing camps, one arguing the real number was close to 50, the other insisting it was nearer to 100. This argument was not polite. Careers were built and destroyed in the process. Conferences turned into verbal battlegrounds. By the early 2000s, better instruments had pushed the community toward a compromise value near 70 kilometers per second per megaparsec. The old war appeared to be finished. It wasn't. A smaller, sharper version of the dispute emerged, one that refused to resolve no matter how much the instruments improved. The disagreement shrank in raw numerical size, but the implications grew more troubling. Both camps now had excellent data. Both methods had been verified repeatedly, and yet they disagreed. Worse, as precision improved, the gap widened rather than narrowed. The two approaches take fundamentally different routes to the same question. The first method looks backward through time as far as light itself allows. The European Space Agency's Planck satellite spent roughly 4.5 years mapping what is called the cosmic microwave background. This is a faint bath of radiation that fills every cubic meter of space. It is the residual glow of the intense heat that existed in the young universe. The radiation was released when the cosmos was about 380,000 years old, the specific moment when space had cooled enough that electrons could bond with protons to form neutral hydrogen atoms. Before that moment, the universe was opaque. After it, light could finally travel freely. From the faint temperature variations imprinted on this radiation, physicists can read the initial conditions of the universe with astonishing precision. They can calculate how dense the early cosmos was, how lumpy, how much of it was ordinary matter, how much was dark matter, how much was radiation. Plug those numbers into the standard cosmological model, run the equations forward nearly 14 billion years, and you get a prediction for how fast space should be expanding today. Planck's prediction settled at approximately 67 kilometers per second per megaparsec. The second approach takes no shortcuts through theory. It measures directly. Adam Riess and his team, working under a project called SHOWS, use what astronomers call the cosmic distance ladder. The name fits the method. It is a chain of overlapping measurement techniques, each calibrated against the previous one, reaching step by step into the depths of space. The first rung uses a type of star called a Cepheid variable. These stars pulse with a steady, predictable rhythm, brightening and dimming on a cycle that can last anywhere from a few days to several months. In 1912, an astronomer named Henrietta Swan Leavitt, while analyzing photographic plates at Harvard College Observatory, discovered something extraordinary. The length of a Cepheid's pulsation cycle is directly tied to its true brightness. Measure how long it takes to complete one pulse, and you know how luminous the star actually is. Compare that true brightness to how bright it looks from Earth, and you can calculate how far away it sits. Leavitt's law turns Cepheids into one of the most powerful measuring tools ever discovered in astronomy. The second rung uses a specific kind of exploding star called a Type 1a supernova. These detonations occur when a white dwarf, the compact corpse of a sun like ours, accumulates material from a companion star until it reaches a critical threshold mass. At that threshold, the star tears itself apart in a runaway thermonuclear explosion. Because the trigger mass is always roughly the same, the brightness at peak is always roughly the same. Astronomers call such objects standard candles. If you know the true brightness of something, you can calculate its distance from how dim it appears. The Cepheids calibrate the supernovae. The supernovae extend the reach of the ladder across hundreds of millions of light years. Combine those distances with how fast the host galaxies are receding, and out pops the Hubble constant. Riess's team arrived at 73, not 67. The universe, by their direct measurement, is expanding about 9% faster than the theoretical prediction. In everyday terms, 9% might sound minor. In a field where measurements routinely achieve accuracy within 1%, a 9% gap between two rigorous independent methods is enormous. It is the equivalent of two independent teams measuring the same building and one declaring it 10 stories tall, while the other insists it is 11, with both teams absolutely certain their tape measure is correct. For years, most cosmologists assumed the disagreement had to be a measurement error. The favorite suspect was something called stellar crowding. Cepheid variables tend to live inside the dense, dusty disks of young, actively star-forming galaxies. When the Hubble Space Telescope photographed these stars, its cameras sometimes blended the light of nearby stars into the Cepheid's own signal, making the variable star appear brighter than it really was. A brighter Cepheid looks closer than it is. Shorter calculated distances produce a higher calculated Hubble constant. The logic was clean. If you fix the blending problem, the gap should vanish. The James Webb Space Telescope was expected to settle the question. Webb orbits the Sun at a gravitational balance point about 1.5 million kilometers from Earth, beyond any atmospheric interference. Its primary mirror measures 6.5 meters across and is coated in gold to optimize its sensitivity to infrared light. Infrared vision is ideal for this problem. Infrared radiation cuts through dust, and Webb's resolution can cleanly separate individual stars in regions that Hubble could only see as blurred smears. If stellar crowding was inflating the Cepheid brightness measurements, Webb would reveal the problem. The Cepheids would appear dimmer, the distances would stretch out, the Hubble constant would fall back towards 67, and the crisis would deflate into a footnote. Some astronomers were already outlining papers describing what the resolution would mean for the field. That resolution never came. Webb confirmed the Hubble Space Telescope's Cepheid measurements with extraordinary precision. The stars looked the same, the distances held. The expansion rate remained at 73. In early 2024, the show's team published their full analysis in the astrophysical journal Letters. They had extended Webb observations across 5 host galaxies, measured nearly 1,000 individual Cepheids, and calibrated the distances to 8 Type 1a supernovae. Their sample reached all the way to a galaxy called NGC 5468, roughly 130 million light-years away. Their conclusion was direct. Systematic measurement error could be ruled out with very high statistical confidence. Riess's reaction to this result was characteristically restrained. With the known errors eliminated, he said, "What remains is the possibility that we have misunderstood the universe." At a cosmology conference in 2019, Riess had asked another Nobel laureate, the particle physicist David Gross, whether the community should start calling the discrepancy a problem. Gross corrected him, "Don't call it a tension. Don't call it a problem. Call it a crisis." 5 years later, that is still the most accurate word for it. But not every astronomer sees the situation the same way. Wendy Friedman at the University of Chicago has spent years building her own independent version of the distance ladder, one designed to rely less heavily on Cepheid stars. Her concern is that Cepheids, despite Leavitt's law, may carry hidden systematic errors that nobody has fully characterized. To guard against that possibility, her team uses additional types of standard candles, red giant stars, which reach a characteristic peak brightness at a specific point in their evolution, and a class called J stars, which are carbon-rich stars typically found in the outer, less crowded regions of galaxies, where dust and blending cause fewer problems. When Friedman's team published their own Webb analysis in August of 2024, the 3 methods they used did not perfectly agree with each other. The red giant and J-star measurements landed around 68 to 70, consistent with the Planck prediction. The Cepheid measurement came in near 72, closer to the show's value, though with larger uncertainties. Their combined results sat around 70, awkwardly between the two camps, unable to fully endorse either side. Saul Perlmutter, another Nobel laureate who reviewed the Friedman data before publication, pointed out something subtle but important. The results suggested internal tension within the star-based measurements themselves, even before comparing them to the cosmic microwave background prediction. That was a different kind of problem. It implied that the cosmic distance ladder, a tool astronomers have trusted for a century, might carry unresolved systematic uncertainties at its very foundation that no single telescope can fix. Riess pushed back. He argued that Friedman's team had used a smaller and potentially unrepresentative sample of Type 1a supernovae, which could bias the result downward. The dispute between the two groups has become one of the most closely watched rivalries in modern science. Two teams of talented, rigorous astronomers looking at the same sky, drawing different conclusions from the same photons. This disagreement matters not only for the Hubble constant itself, but for what the Hubble constant represents. If the universe genuinely is expanding about 9% faster than the standard model predicts, then something is missing from our understanding of how the cosmos evolved. Whatever that missing thing is, it would have to be fundamental: a new behavior for dark energy, a new type of particle that existed briefly after the Big Bang, a modification to the laws of gravity at cosmological scales, or something nobody has yet conceived. One of the more serious proposals is called early dark energy. The standard model assumes that dark energy, the mysterious force driving the accelerating expansion of the universe, has always behaved exactly as it behaves today: constant, uniform, identical across all space and all time. But what if, in the first few 100,000 years after the Big Bang, before the cosmic microwave background was released, dark energy had a brief burst of additional activity and then went quiet? Mark Kamienkovsky, a cosmologist at Johns Hopkins who helped develop the idea, has described this scenario as the universe receiving an unexpected kick just after its birth. A short surge of early dark energy would have slightly altered the size of sound waves traveling through the primordial plasma. That in turn would have changed the scale of the features Planck measured in the cosmic microwave background. Those shifted features would ripple through the model's calculations, pushing the predicted expansion rate upward, potentially closing the gap with the value Riess measures today. Nobody knows whether early dark energy is real. It has never been detected directly. The proposal produces additional testable predictions that future instruments will examine, but it remains one of the few theoretical modifications that could resolve the Hubble tension without dismantling the rest of the standard model's impressive predictive record. Its appeal is that it adds something rather than breaks something. Other proposals are less conservative. Some theorists argue that dark energy is not constant at all, but a dynamic field that evolves across cosmic history. Others propose modifications to general relativity at scales where Einstein's theory has never actually been tested with the precision it has achieved within the solar system. A few theorists have even suggested that the universe might be subtly different in different directions, violating a foundational assumption called the cosmological principle, which states that the cosmos should look essentially the same from any vantage point. All of these ideas are speculative, none are confirmed, but they are being taken seriously because the data is demanding it. And then, before astronomers had fully processed the Hubble tension, Webb delivered a second surprise. Almost from the moment it began examining the deep universe, Webb found galaxies that appeared far too massive to exist at the distances where they were detected. The telescope was designed to look back to within a few 100 million years of the Big Bang, to watch the very first galaxies condense out of the primordial darkness. The expectation was that these early galaxies would be small, irregular, chaotic, nothing like the grand spiral and elliptical structures we see nearby today. The predictions were specific. At redshifts corresponding to a universe less than 1 billion years old, galaxies should be faint, compact, and lightweight. What Webb actually found were galaxies that rivaled the Milky Way in mass, apparently fully assembled and luminous at cosmic epochs where the standard model did not leave enough time to build them. Mike Boylan-Kolchin, an astronomer at the University of Texas at Austin, analyzed 6 of the most extreme early galaxy candidates from Webb in a study published in Nature Astronomy. His conclusion was blunt. To construct galaxies that massive in the time available, nearly every atom of gas within their surrounding dark matter halos would have had to convert into stars. Under normal conditions, the efficiency of that conversion sits around 10%. The other 90% either gets too hot, gets blown away by radiation from newly formed stars, or simply never collapses. These candidate galaxies appeared to be operating at 100% efficiency. No known model produces that, not even close. The reaction across the field was a mix of excitement and alarm. If these galaxies were real, and really that massive, then either our understanding of how galaxies form was badly incomplete, or the timeline encoded in the standard model itself needed revision. Then came a correction, and it illustrates how carefully Webb's raw data has to be interpreted. Katherine Chworowski, a graduate student at the University of Texas, led a study in mid-2024 that re-examined the massive early galaxy candidates. She found that many of them were being fooled by their own black holes. The galaxies in question, nicknamed little red dots by astronomers because of their compact appearance and characteristic infrared color, contained supermassive black holes actively and voraciously devouring surrounding gas. As material spirals toward a black hole, it forms a whirling disk of gas and dust. Friction within this disk heats the material to extreme temperatures. The heated gas radiates enormous amounts of light, sometimes brighter than all the stars in a galaxy combined. From billions of light years away, through Webb's cameras, a galaxy containing an actively feeding black hole at its center can look almost identical to a galaxy containing 10 times as many stars. Telescopes measure brightness. Brightness is usually a reliable proxy for stellar mass. In these cases, it was not. The black hole was producing the light of billions of suns, inflating the galaxy's apparent mass the way a single bright lamp inflates the apparent temperature of a room. Once the contaminated little red dots were removed from the sample, the remaining galaxies fit reasonably well within the standard model's predictions. Stephen Finkelstein, Chworowski's advisor, put it plainly. "There is no crisis in terms of the standard cosmological model," he said, "based on what the galaxies at those distances are actually showing us." The story did not end there though. Even after the contaminated sample was removed, roughly twice as many massive early galaxies remained as the standard model had predicted. The excess was not catastrophic, not large enough to break the model, but it was consistent and it was real. Chworowski herself suggested that stars may have formed more efficiently in the very early universe than they do today. Denser, more tightly packed conditions shortly after the Big Bang may have made it harder for gas to escape during star formation, allowing the process to run closer to its theoretical maximum. It is a plausible explanation, but it still requires adjustments to how we model galaxy formation in the first billion years. Then, in early 2025, Webb delivered yet another surprise. A massive spiral galaxy, quickly nicknamed the Big Wheel, was found to exist within the first 2 billion years of cosmic history. Spiral structure is not something that forms quickly. Building a coherent rotating disk requires a relatively quiet gravitational history, steady accretion of gas without violent mergers, and enough time for differential rotation to wind stellar arms into their characteristic pattern. In a young, turbulent universe dominated by rapid mergers and chaotic growth, mature spirals are not supposed to appear. Not yet. Temiya Nanayakura, one of the astronomers at Swinburne University of Technology who discovered the Big Wheel, noted that the galaxy had either assembled its mass in an unusually orderly way or formed most of its stars in place without the violent collisions that typically build large galaxies under the standard model. Either explanation requires revisions to how we think early galactic structure develops. At the same time, a separate team at Cambridge University used Webb to study over 250 galaxies from the same cosmic era and found the opposite pattern. Most of the early galaxies they examined were chaotic, turbulent, clumpy systems that had not settled into smooth rotating disks at all. So the early universe apparently contained both messy adolescent galaxies and at least one remarkably mature spiral coexisting within the same epoch. That is a contradiction the standard model does not handle elegantly. And none of this addresses the elongated galaxies. A study published in Nature Astronomy in late 2025, led by Alvaro Pozo and including researchers from MIT, Harvard, and the Academia Sinica Institute of Astronomy and Astrophysics in Taipei, found that many young galaxies observed by Webb appear strikingly elongated, stretched along one direction like cosmic cigars. These prolate shapes extended along a single axis rather than flattened into a disk, do not match the predictions of cold dark matter models, which form the structural scaffolding of the standard cosmology. Cold dark matter is what the standard model proposes as the dominant form of matter in the universe. The word cold does not refer to temperature in the ordinary sense. It refers to the speed of the dark matter particles relative to the speed of light. Cold dark matter particles are assumed to be slow-moving, heavy, and essentially collisionless. These properties determine how dark matter clumps together in the early universe and how those clumps seed the formation of galaxies. The elongated shapes Webb keeps finding do not match what cold dark matter predicts. They do, however, match predictions from two alternative models: warm dark matter, in which the particles are lighter and move faster, and wave dark matter, sometimes called fuzzy dark matter, in which dark matter behaves as a quantum wave field with a characteristic wavelength on astronomical scales. In both of these alternatives, the filaments of large-scale cosmic structure are smoother, and gas and stars can flow along them in elongated streams, naturally producing the prolate shapes Webb is observing. The distinction is not a minor cosmetic detail. Cold dark matter is not just one ingredient among many in the standard model. It is the scaffolding. It determines where galaxies form, how they cluster, how the vast cosmic web looks on the largest scales. Dark matter makes up roughly 27% of everything in the universe. If its fundamental properties differ from what cold dark matter models assume, the consequences propagate through nearly every prediction cosmology makes. Those consequences include the expected mass distribution of galaxy clusters, the predicted number of dwarf galaxies orbiting larger ones, which has already been a source of tension for years in what astronomers call the missing satellites problem, and the way gravitational lensing bends light around massive objects. You cannot alter the foundation of a physical framework and expect everything built on top of it to stay in place. So where does all of this leave the standard model? It is important to be honest about the situation. The standard model of cosmology is not collapsing, it is not dying, it is not even close to being replaced. It remains the most precisely successful theory of the large-scale universe ever constructed. It correctly predicted the abundances of hydrogen, helium, and lithium produced in the first 3 minutes after the Big Bang, matching observations to within a percent. It explains the detailed structure of the cosmic microwave background with stunning precision. It correctly predicts the clustering of galaxies across hundreds of millions of light years. It predicted the existence of dark energy years before the supernova observations of 1998 confirmed it. No competing theory matches that record. None. But the model is showing fractures that were not visible a decade ago, and those fractures are widening rather than closing as instruments improve. The Hubble tension sits at the top of the list. A 9% disagreement between two rigorously independent measurement methods confirmed by two separate flagship space telescopes is not a rounding error. It is a signal. There is also the early universe galaxy problem, which is not fully resolved even after correcting for black hole contamination. There are the elongated prolate galaxies, suggesting dark matter may not be cold. There is the cosmic web structure on the largest scales, which some surveys find slightly different from what the standard model predicts. And there is a second, quieter tension that has received far less public attention. It is called the S8 tension. The S8 parameter describes how clumpy the universe is, how much matter has gathered into dense concentrations of galaxies and galaxy clusters versus how much remains spread smoothly through space. The standard model predicts a specific level of clumpiness based on the initial conditions measured in the cosmic microwave background. When astronomers measure that clumpiness directly, using techniques like weak gravitational lensing, they consistently find slightly less clustering than the model expects. Adam Riess has described the S8 tension as the little sibling of the Hubble tension. Less dramatic, less statistically decisive, but persistent, and pointing in the same general direction. If both tensions turn out to be real, they may be symptoms of the same underlying problem. Two cracks in the same wall, both hinting at something missing from the physics. What is striking about this moment in cosmology is that the anxiety within the field is productive rather than paralyzing. There is no panic. There is no sense that the entire framework is crumbling. The prevailing mood is closer to focused unease, the feeling of having almost finished a complicated jigsaw puzzle and then discovering that a piece does not fit. Not because the puzzle itself is wrong, but because the picture printed on the box might not be the complete image. That distinction matters. A crisis in fundamental physics is not the same as a failure. Throughout the history of science, The moments that look most like failure often turn out to be the points where real progress begins. The physics of the late 19th century appeared finished and triumphant, right up until it was not. The ultraviolet catastrophe and blackbody radiation, the null result of the Michelson-Morley experiment, the unexplained precession of Mercury's orbit, each of these was a small, stubborn discrepancy that refused to go away. Each turned out to be a door. The quantum revolution, special relativity, and general relativity did not emerge from confirmation. They emerged from contradiction. Cosmology has its own history of this pattern. In the 1990s, the field faced a different crisis. Measurements of stellar ages suggested that the oldest stars were older than the universe itself, which was plainly impossible. Stars cannot be older than the cosmos that produced the nuclear fuel they burn. Something was deeply wrong with either the stellar age estimates or the cosmological model. The resolution, the discovery in 1998 that the universe's expansion is accelerating, driven by what we now call dark energy, did not merely fix the age problem. It revealed that 68% of the entire energy content of the universe had gone completely undetected and unaccounted for in every prior cosmological theory. What looked like a fatal inconsistency turned out to be the shadow of something enormous. The field did not shrink from that discovery. It expanded, along with our conception of what the universe is. What is happening now may be structurally similar. The Hubble tension may be telling us that dark energy is not what we think it is, that it does not behave as a fixed cosmological constant, but evolves over cosmic time. The early galaxy problem may be telling us that the rules governing how gas collapses into stars in the early universe were different from what our models assume. The elongated galaxy shapes may be telling us that dark matter is lighter, fuzzier, or more wave-like than the cold dark matter paradigm allows. The S8 tension may be pointing at a problem in how gravity behaves on cosmic scales, or in how dark matter behaves there, or both. Or all of these tensions may share a single source that nobody has yet identified, a missing piece so fundamental that once it is found, the entire picture will rearrange itself into a new and deeper coherence. New instruments are coming, and their data will be decisive. NASA's Nancy Grace Roman Space Telescope, designed as a successor to Hubble for wide-field infrared surveys, will conduct massive surveys of galaxy distribution across billions of light-years, specifically to probe the nature of dark energy and whether it has changed across cosmic time. The European Space Agency's Euclid mission is already operating, mapping the geometry of the universe on scales no previous telescope has attempted. Its goal is to measure the pattern of galaxy clustering and gravitational lensing across 10 billion years of cosmic history, producing a three-dimensional map of how dark matter and dark energy have shaped the large-scale structure of the cosmos. The data will test the Standard Model's predictions with precision that will either confirm or decisively challenge its core assumptions. The Gaia Space Telescope, while primarily a stellar survey instrument, is producing the most precise geometric distance measurements to Cepheid variables ever achieved. These measurements will let astronomers calibrate the bottom of the cosmic distance ladder with a precision that bypasses many of the systematic uncertainties that currently separate the Riess and Friedman teams, potentially settling the question of whether the discrepancy lies in the Cepheid measurements themselves. On the ground, the Atacama Cosmology Telescope has already produced the most detailed ground-based map of the cosmic microwave background ever made. Its latest data release slightly revised the Planck prediction for the Hubble constant upward, nudging it closer to 70. Not enough to close the gap, but enough to confirm that the tension is real and to narrow the range of explanations that could account for it. The Vera Rubin Observatory in Chile, which will conduct the legacy survey of space and time over the next decade, will observe billions of galaxies and tens of thousands of Type 1a supernovae, providing an independent measurement of the Hubble constant with statistical power that dwarfs every prior effort combined. All of this infrastructure is either already operational or coming online within the next few years. The current decade will not end with the Hubble tension unresolved. Either the gap will close, revealing a systematic error everyone missed, or it will deepen, demanding new physics to explain it. The universe has been expanding since the Big Bang. The question now at the center of cosmology is whether it is expanding according to the rules we have written or according to rules we have not yet found. There is something remarkable about this situation when you step back from the technical details. Human beings, on a rocky planet orbiting an ordinary star in the suburbs of a perfectly unremarkable spiral galaxy, have built instruments sensitive enough to detect the expansion of space itself and measure it to within a few percent. We have traced the history of the cosmos from the first fraction of a second after its birth to its present state 14 billion years later, using light that has been traveling for billions of years to reach our detectors. And having achieved that level of precision, we have found that the universe does not quite match our predictions by 9%, by twice as many galaxies as expected, by shapes that do not fit the models. That 9% is not an embarrassment. It may be the most valuable number in science right now because it means the map is wrong in a specific, identifiable way, and specific wrongness has always pointed towards specific discovery. The standard model will either be corrected, extended, or replaced. History suggests the first option is most likely. The correction, when it comes, will probably be something that in retrospect looks obvious, something hiding in the data we have been looking at without fully understanding. A different behavior for dark energy in the early universe, a slightly different mass for dark matter particles, a modification to how efficiently early galaxies turned gas into stars, or it will be something nobody has yet thought of. Something that arrives from a direction nobody is watching. That is the history of physics. The answer usually comes from the direction nobody expected. What we know right now is that two of the most powerful instruments humanity has ever pointed at the sky are telling us, with high statistical confidence, that our model of the universe is missing something real. The James Webb Space Telescope and the Hubble Space Telescope, cross-checked against each other, find the same expansion rate. The Planck satellite, cross-checked against theoretical models of extraordinary precision, finds a different one. Those two answers cannot both be right, and they are both, as far as anyone can tell, built on excellent science. The universe, in other words, is disagreeing with itself, or rather, it is disagreeing with us. And the gap between what it is and what we thought it was is where the next version of cosmology will be found. To fully appreciate what these telescopes are revealing, it helps to understand how strange the standard model's ingredients actually are when you look at them directly. The model that predicts a Hubble constant of 67 is called lambda CDM. Lambda is the symbol for the cosmological constant, Einstein's original term for the energy of empty space, which is what we now call dark energy. CDM stands for cold dark matter. Together, these two components make up roughly 95% of everything in the universe. Dark energy accounts for about 68%. Cold dark matter accounts for about 27%. Everything you have ever seen, touched, breathed, burned, or built, every star, every planet, every atom of every element adds up to roughly 5% of the total. That asymmetry is not intuitive. We are, in the most literal sense, the rare exception in a cosmos dominated by things we cannot see, cannot touch, and cannot directly detect. Every instrument we have built, every telescope we have launched, every particle accelerator we have operated has been probing that 5%. The other 95% has been inferred from its gravitational effects. Dark matter is inferred because galaxies spin too fast. A galaxy like the Milky Way, if it contained only the mass we can see, would tear itself apart. The stars in the outer disk would escape their orbits because the gravitational pull from the visible mass at the center would not be strong enough to hold them. The fact that they do not fly apart means there must be additional mass we cannot see, a halo of dark matter surrounding and permeating the galaxy, providing the gravitational glue that keeps the spiral structure intact. This explanation was developed primarily by Vera Rubin and Kent Ford in the 1970s, who mapped the rotation curves of dozens of galaxies and found the same result everywhere. The outer regions of galaxies were rotating just as fast as the inner regions, when they should have been rotating slower if gravity fell off with distance the way it does in our solar system. The only explanation that worked was unseen mass, a lot of it. Roughly 5 times more than the visible matter. Dark matter has now been confirmed through multiple independent lines of evidence. The bending of light around galaxy clusters through gravitational lensing reveals more mass than the visible galaxies can account for. The structure of the cosmic microwave background encodes the signature of dark matter's influence in the early universe. The large-scale architecture of the cosmos, the intricate web of galaxy filaments and voids spanning hundreds of millions of light years, matches precisely the pattern that cold dark matter simulations produce. The evidence for dark matter's existence is not in question. What is in question now is what dark matter actually is. Cold dark matter models assume the particles are heavy, slow-moving relative to the speed of light, and effectively point-like in their behavior. They clump together under gravity in a specific way, forming halos with a characteristic density profile, dense at the center and thinning toward the edges along a predictable mathematical curve. These halos seed galaxy formation. Gas falls into them, cools, and collapses into stars. The halo's mass and structure determine the galaxy that forms within it. This works remarkably well on large scales. But on the scales of individual galaxies and their smaller companions, cold dark matter predictions have faced persistent problems for decades. The models predict far more small dark matter clumps than we observe as small galaxies. This is the missing satellites problem. The models also predict that the density of dark matter at the very centers of galaxies should rise to what is called a cusp, a sharp peak. But observations of many dwarf galaxies suggest the dark matter density flattens at the center into a core rather than rising to a cusp. And the models predict that the most massive satellite galaxies of the Milky Way should be denser than they actually are. These are known collectively as the small-scale structure problems of cold dark matter. For years, astrophysicists have argued that these discrepancies might be resolved by better modeling of how gas, star formation, and supernova feedback reshape the dark matter distribution inside galaxies. When stars form and explode, they push gas around, and the moving gas can gravitationally drag dark matter with it, smoothing a central cusp into a core. Whether this kind of feedback is sufficient to explain all the small-scale tensions is still debated. Now Webb is adding elongated galaxy shapes to the list of things that warm or wave dark matter explains better than the cold version does. Wave dark matter, sometimes called fuzzy dark matter, is perhaps the most exotic of the mainstream alternatives. In this model, dark matter is an extremely light particle, a boson with a mass roughly 22 orders of magnitude smaller than the electron. At such a tiny mass, quantum mechanical effects become relevant on astronomical scales. The wavelength associated with the particle, the scale over which quantum wave behavior becomes important, would be roughly a kiloparsec, or about 3,000 light-years. On scales smaller than that, dark matter would behave not as a collection of individual particles, but as a coherent quantum wave field, unable to clump tightly because quantum pressure resists compression below the characteristic wavelength. This behavior would naturally resolve the cusp-core problem in dwarf galaxies. The central density cannot rise to a cusp because quantum pressure fights back. It would reduce the number of small satellite galaxies because small dark matter halos below the quantum scale simply would not form. And it would create the kind of smooth, coherent filamentary structure along which gas could flow and form the elongated prolate galaxy shapes that Webb is finding in the early universe. The challenge for fuzzy dark matter is that its characteristic scale may be wrong. Some observations of the Lyman alpha forest, the pattern of hydrogen absorption imprinted on the spectra of distant quasars, suggest the quantum wavelength would need to be much smaller than a kiloparsec to be consistent with observed structure on those scales. If that is right, fuzzy dark matter cannot solve the small-scale problems and the appeal of the model weakens considerably. This is the current state of dark matter physics. Multiple models are viable, multiple observations favor different alternatives. No single candidate perfectly explains everything. And until a dark matter particle is directly detected in a laboratory experiment, the field will remain in a state of productive tension. The dark energy side of the equation is, if anything, more mysterious. When dark energy was first confirmed in 1998 by the High-Z Supernova Search Team and the Supernova Cosmology Project, both groups doing exactly the kind of Type 1a supernova distance measurements that Riess's team continues today, the discovery was that the expansion of the universe is accelerating, not just expanding, but expanding faster and faster over time, as if something is pushing galaxies apart at an ever-increasing rate. Saul Perlmutter, Brian Schmidt, and Adam Riess shared the Nobel Prize in Physics in 2011 for this discovery. It was one of the most unexpected results in the history of cosmology. Before 1998, everyone assumed the universe's expansion was slowing down. Gravity should decelerate it. All the matter in the universe is pulling on all the other matter. The expansion should be running out of steam. Instead, it was speeding up. Einstein had actually predicted the possibility decades earlier, though for entirely the wrong reasons. When he first applied his general theory of relativity to the universe as a whole in 1917, his equations kept producing a dynamic universe, one that was either expanding or contracting, never static. At the time, conventional wisdom held that the universe was eternal and unchanging. Einstein found this so unacceptable that he added an extra term to his equations, the cosmological constant, a form of energy inherent to empty space that would counteract gravity and hold the cosmos in a stable state. When Hubble discovered in 1929 that the universe was in fact expanding, Einstein reportedly called the cosmological constant the biggest blunder of his life and removed it from the equations. Then, in 1998, it came back. The acceleration of the universe required exactly the kind of repulsive energy the cosmological constant represented. Empty space itself appeared to contain energy that does not dilute as the universe expands. Unlike the energy of radiation or matter, which spreads thinner as space stretches, dark energy maintains a constant density. This means that as the universe grows larger, the total amount of dark energy grows with it, eventually overwhelming the decelerating pull of matter and causing the expansion to accelerate. This is the lambda in lambda CDM, a cosmological constant, a fixed energy density of empty space, unchanging and uniform everywhere in the universe. It fits the observations, the supernova data, the cosmic microwave background, the clustering of galaxies. Everything is consistent with a cosmological constant. But there is a profound theoretical problem with this picture. When particle physicists calculate what the energy density of empty space should be from first principles using quantum field theory, they get an answer roughly 10 to the 120th power times larger than what we observe. That discrepancy, 120 orders of magnitude, is the largest single disagreement between theory and observation in the history of physics. It is called the cosmological constant problem, and it has been unsolved since the 1990s. The resolution most physicists silently accept is an unsatisfying one. Some unknown mechanism must cancel out almost all of the quantum vacuum energy, leaving behind only a tiny residual that matches what we observe. Nobody knows what this mechanism is. No theory predicts it. It simply has to be true because we observe the universe to be the way it is. If the Hubble tension is telling us that the expansion history of the universe is different from what lambda CDM predicts, it may also be telling us something about this deeper problem. If dark energy is not a constant, but a field that evolves over time, its behavior in the early universe would have been different from its behavior today. That difference would change the expansion history in exactly the way that could produce the Hubble tension. It would also mean that dark energy is not the fixed cosmological constant of Einstein's equations, but a dynamical entity, what theorists call quintessence, a slowly rolling scalar field that dilutes as the universe expands but more slowly than ordinary matter. Early results from the Baryon Oscillation Spectroscopic Survey and subsequent analyses using galaxy clustering data have hinted at exactly this kind of evolution, a slight departure from a pure cosmological constant. The Dark Energy Spectroscopic Instrument, currently operating in Arizona on the 4-meter Mail telescope at Kitt Peak, is conducting the largest three-dimensional survey of galaxy positions ever attempted, covering tens of millions of galaxies across more than 11 billion years of cosmic history. Its goal is to map the history of the universe's expansion and determine whether dark energy has changed over time. First results from this instrument, released in 2024, showed intriguing hints that dark energy might be evolving, with its properties deviating slightly from the values predicted by a pure cosmological constant. This is not yet confirmed. The statistical significance of the deviation is suggestive rather than definitive. More data is coming, but if the trend holds up, it would mean that both the Planck prediction and the lambda CDM framework need revision, not because the underlying physics is wrong, but because the specific model we have been using to describe dark energy is too simple. It would also change the fate of the universe. A true cosmological constant expands the universe forever at an ever-accelerating rate. Eventually, in tens of billions of years, every galaxy beyond our local group will have receded beyond our cosmological horizon, invisible and unreachable, leaving our galaxy effectively alone in observable space. Trillions of years later, the stars will burn out one by one, and the universe will approach a cold, dark, diffuse equilibrium sometimes called the heat death. A dynamical dark energy field, depending on how it evolves, could produce a very different ending. If dark energy grows stronger over time, the expansion could eventually become so violent that it tears apart not just galaxy clusters, but individual galaxies, then solar systems, then planets, then atoms themselves, in an event theorists call the Big Rip. If dark energy weakens, the expansion could slow, stop, and reverse, leading to a big crunch, the universe collapsing back on itself in a mirror image of the Big Bang. We do not know which of these futures we inhabit. We do not even know which version of dark energy we have. That uncertainty is not a flaw in our science. It is an accurate description of the current state of knowledge. What can be said is that the telescopes and surveys now operating or soon to come online will dramatically narrow the possibilities. By the end of this decade, cosmologists should know whether dark energy is constant or evolving, whether dark matter is cold or warm or wave-like, and whether the Hubble tension is a systematic error or a genuine sign of new physics. Those are not small questions. They are the central questions of fundamental cosmology. The cosmic microwave background deserves more attention here because it is where the Standard Model's greatest predictive triumphs lie, and therefore where a departure from the Standard Model would be most significant. When the universe was 380,000 years old, it underwent a phase transition called recombination. Before that moment, the cosmos was a plasma. Protons and electrons moved freely, separated by the intense heat. Radiation was tightly coupled to matter. The whole system was opaque to light. After recombination, neutral hydrogen formed, radiation decoupled from matter, and the universe became transparent for the first time. That first light, released during recombination, has been traveling through space ever since. Its wavelength has stretched along with the expansion of the universe, shifting from visible and infrared wavelengths down into the microwave range. Today it fills the sky as a faint uniform glow in every direction. If your eyes could see microwaves, the entire sky would shine with the afterglow of creation. The pattern of temperature variations in this background radiation, tiny fluctuations of about 1 part in 100,000 from one point on the sky to another, encodes the physics of the early universe with extraordinary precision. The positions of peaks and troughs in the angular power spectrum of these fluctuations are determined by the interplay of gravity pulling matter together, radiation pressure pushing it apart, and the speed at which sound waves could propagate through the primordial plasma. The Planck satellite measured this combination. From those 6 parameters, everything else in the Standard Model can be derived, including the predicted Hubble constant of 67. That derivation works because the Standard Model is a complete framework. It specifies all the physics between the recombination epoch and today. If the framework is correct, the Hubble constant derived from the early universe must match the one measured directly today. They do not. Something happened between recombination and now that the Standard Model does not account for. The early dark energy hypothesis is appealing precisely because it inserts a modification at the right moment. By adding a brief episode of additional expansion energy in the period just before recombination, you can change the size of the sound horizon, the characteristic scale of those acoustic oscillations imprinted on the cosmic microwave background. Changing the sound horizon changes the inferred distances to features in the cosmic microwave background. Changing those distances within the standard analysis framework shifts the inferred Hubble constant upward. The problem is that early dark energy, while it helps with the Hubble tension, tends to make the S8 tension worse. The additional energy in the early universe increases the predicted clustering of matter, pushing the prediction further from the observed value rather than closer. A solution that fixes one tension by aggravating another is not satisfying. It might just be rearranging the discrepancy rather than resolving it. This is a general feature of attempts to modify the Standard Model. The model is internally consistent enough that changing one ingredient has cascading effects throughout all of its predictions. Every proposed modification has to pass not just the Hubble constant test, but the entire suite of cosmological observations that the Standard Model currently explains with high precision. That constraint is both a strength and a frustration for theorists trying to build something new. It is also worth stepping back and appreciating what the Standard Model gets right, because in the current climate of scientific tension, it is easy to lose perspective. The primordial nucleosynthesis predictions of the Standard Model, the abundances of hydrogen, helium, and trace amounts of deuterium and lithium produced in the first 3 minutes after the Big Bang, match observations to remarkable precision. About 75% of ordinary matter came out as hydrogen and about 25% as helium. The Standard Model predicts this ratio from the competition between the expansion rate and the nuclear reaction rates governing proton and neutron conversion. It works because the expansion rate, the temperature history, and the nuclear physics are all well understood. This agreement extends to deuterium, which is a particularly sensitive probe because deuterium is easily destroyed by further nuclear reactions. Its present abundance reflects very precisely the conditions in the first few minutes. The model's prediction matches the observed deuterium abundance to within 1%. The baryon acoustic oscillation signal, the characteristic clustering scale imprinted on the distribution of galaxies today by the same sound waves that produce the cosmic microwave background peaks, has been measured in multiple galaxy surveys and matches the standard model prediction with high precision. This measurement is entirely independent of the Hubble constant controversy because it measures the shape of the clustering pattern, not the absolute scale. The large-scale structure of the universe, the cosmic web of filaments, walls, sheets, and voids that appears when you map the positions of millions of galaxies, is beautifully reproduced by simulations that start from the density fluctuations measured in the cosmic microwave background and evolve them forward under gravity with cold dark matter. These simulations, run on the largest supercomputers in the world, produce virtual universes that look statistically indistinguishable from the real one when compared on scales larger than a few tens of millions of light years. That is not a coincidence. That is evidence that the physics encoded in the standard model is genuinely correct, at least in its core features. The question is not whether the model is right, it is whether it is complete. The history of physics suggests it is not. Not because the standard model is wrong, but because every successful physical theory has eventually turned out to be a limiting case or approximation of something deeper. Newtonian mechanics is an approximation of special relativity, valid when velocities are small compared to the speed of light. Special relativity does not account for gravity. It is a limiting case of general relativity, valid in the absence of strong gravitational fields. General relativity and quantum mechanics, the two pillars of modern physics, are mathematically incompatible with each other and cannot both be fully correct. The reconciliation of these two theories into a quantum theory of gravity remains the deepest unsolved problem in fundamental physics. Cosmology sits at the intersection of both. The earliest moments of the universe, the first fraction of a second after the Big Bang, required both quantum mechanics and gravity to describe. Our standard cosmological model begins just after that epoch, after the quantum gravity era has ended and the universe is large enough and cool enough to be described by classical general relativity combined with quantum field theory corrections. The physics of that earliest epoch is unknown, and whatever happened there set the initial conditions for everything that followed. If those initial conditions were even slightly different from what the standard model assumes, if there were new particles, new fields, or new symmetry-breaking events during the quantum gravity era, those differences could propagate forward through the entire subsequent history of the universe, appearing today as small but persistent discrepancies in things like the Hubble constant and the clumpiness of matter. This is why the tensions matter so much. They may be the echoes of physics that happened in the first instant after the Big Bang, physics we cannot probe directly with any instrument, showing up in the expansion history and structure of the universe today. If so, the Hubble tension is not just a problem for cosmology, it is a window into the highest energy physics that has ever existed. The James Webb Space Telescope continues to accumulate data. Its operational lifetime is currently estimated at about 20 years, limited by the fuel supply needed for the small station-keeping maneuvers that hold it at its gravitational balance point 1.5 million kilometers from Earth. In the years ahead, it will push the sample of early galaxies deeper in time and lower in mass, refining the statistics that will tell us definitively whether the early universe galaxy problem is a real challenge to the standard model or an artifact that resolves with better data. It will also probe the interstellar medium of early galaxies in ways that have never been possible, measuring chemical abundances, star formation rates, and dust properties with the precision needed to constrain the physics of galaxy formation at cosmic dawn. To appreciate how confident scientists are that the Hubble tension is real, it helps to understand the statistical language they use. When scientists report a measurement or a discrepancy, they express their confidence in terms of sigma, the Greek letter representing the standard deviation in a normal distribution. A 1 sigma discrepancy means there is roughly a 32% chance the result could arise from random fluctuation alone. 2 sigma means about 5%. 3 sigma, the threshold sometimes called evidence in particle physics, means about a 3 in 1,000 chance of random fluctuation. 5 sigma, the gold standard for a discovery in high-energy physics, corresponds to roughly a 1 in 3.5 million chance that the result is a statistical fluke. The Hubble tension is currently sitting at around 5 sigma. It has been growing steadily from a 2 sigma hint in the early 2010s to 3 sigma to 4 sigma and now to 5. Each time a new measurement has come in, instead of the tension relaxing, as one might expect if it were a measurement artifact, it has sharpened. The most recent Webb data has not shrunk the gap. It has confirmed it. 5 sigma does not mean certainty. It means that if the standard model were correct and there were no new physics, the probability of observing this discrepancy by chance is roughly 1 in 3.5 million. That is not zero, but it is small enough that the scientific community has moved beyond asking whether the tension is real and toward asking what is causing it. The history of the Hubble tension is itself worth tracing because it illustrates how scientific confidence accumulates. In the 1990s, distance measurements were still primitive enough that both sides of the old debate, those who believed the Hubble constant was closer to 50 and those who believed it was closer to 100, could plausibly claim the data supported their view. The uncertainty bars on individual measurements were enormous. Systematic errors, from dust extinction to Cepheid calibrations, were imperfectly understood. The field was, in a technical sense, not mature enough to resolve the question. The decisive intervention came from the Hubble Space Telescope, specifically from its key project, a major observing program in the 1990s dedicated entirely to measuring Cepheid variables in distant galaxies with enough precision to determine the Hubble constant to within 10%. The project was led by Wendy Friedman, the same astronomer who is now the most prominent skeptic of the current tension value. The key project's final answer, published in 2000, was 72 plus or minus 8. The uncertainty was large enough to be consistent with anything from 64 to 80, but the central value was there and consistent with what subsequent measurements would find. Over the following decade, the uncertainty shrank. The Wilkinson Microwave Anisotropy Probe, a cosmic microwave background mission launched in 2001, provided the first precise constraint from the early universe. Its final results gave a Hubble constant of about 71, consistent with the direct measurement. Then Planck launched in 2009 and measured the cosmic microwave background with unprecedented precision. Its first results, released in 2013, produced a Hubble constant of 67, not 71. The central value had moved. At the same time, Riess's team was improving their direct measurement with the Hubble Space Telescope. By 2016, they were reporting 73. The gap between 67 and 73 was not enormous in absolute terms, but the uncertainties on both measurements had shrunk so much that the two values were clearly incompatible. The tension stood at 3 sigma. In 2019, with more data, Riess's team pushed the significance to 4 sigma. The tension was real, persistent, and getting worse. That was when David Gross told the field to stop calling it a problem and start calling it a crisis. Webb was the next test, and Webb confirmed the distance ladder. What is particularly significant about that confirmation is that it addressed the single most popular explanation for the tension, stellar crowding, and photometric contamination of the Cepheid measurements. Webb's infrared sensitivity was designed precisely to cut through dust and distinguish individual stars in crowded environments. If the Cepheid distances were being systematically overestimated because of blending, Webb would have revealed it. The distances would have stretched, the inferred expansion rate would have dropped, and the Hubble constant would have fallen. Instead, the distances held. The Hubble constant stayed at 73, the most targeted check available, using the most powerful telescope ever built, found no systematic error. That is what transformed the tension from a measurement dispute into a physics problem. There is one more systematic check that has not been fully applied yet, and it involves the bottom of the distance ladder, the parallax measurement of Cepheids within our own Milky Way. Parallax is the most direct method of measuring stellar distance. Observe a nearby star from opposite sides of Earth's orbit around the Sun, separated by 6 months, and measure the tiny shift in the star's apparent position against the background of more distant stars. The shift is larger for nearby stars and smaller for distant ones. Geometry converts the shift directly into distance without any astrophysical assumptions. Parallax measurements of Cepheids in the Milky Way anchor the entire period luminosity relationship that Leavitt discovered. If those Milky Way Cepheid parallaxes are wrong, every distance derived from Cepheid variables is wrong, and the Hubble constant derived from the full distance ladder is wrong. The Gaia Space Telescope, launched in 2013, is the most precise parallax machine ever built. It has measured the positions and motions of nearly 2 billion stars with micro-arcsecond precision, a level of angular resolution roughly equivalent to spotting a coin on the Moon from Earth. Gaia's full Cepheid parallax catalog, which will give definitive geometric distances to hundreds of Milky Way Cepheids, will provide the most rigorous calibration of the distance ladder's bottom rung ever attempted. If Gaia's Cepheid parallaxes agree with what is currently used in the distance ladder, the Hubble constant of 73 is confirmed at the most fundamental level possible. If they disagree, the distance ladder needs recalibration and the tension may partially or fully dissolve. The outcome of the Gaia Cepheid analysis is one of the most anticipated results in cosmology, not because anyone expects a dramatic surprise, but because it will remove the last major argument available to those who still believe the tension can be explained by systematic measurement error. The gravitational wave detectors that have been operating since 2015 offer another angle on the Hubble tension that is worth examining. When two black holes or two neutron stars spiral together and merge, they release enormous amounts of energy as gravitational waves, ripples in space-time itself that spread outward at the speed of light. The amplitude of those waves, how strongly they stretch and compress space as they pass, depends on the masses of the merging objects and how far away the merger occurred. This means that gravitational wave events are a kind of standard siren, analogous to a standard candle, but requiring no calibration against other distance indicators and no assumptions about stellar physics or extinction by dust. If you observe a gravitational wave event and can identify the galaxy it came from, you can measure the recession speed of that galaxy from its spectrum and the distance from the gravitational wave amplitude. Combining those two numbers gives you the Hubble constant directly through a completely independent path. In 2017, the LIGO and Virgo gravitational wave detectors observed the merger of two neutron stars, an event designated GW170817. Remarkably, the event was also detected across the electromagnetic spectrum, from gamma rays to radio waves, and the host galaxy NGC 4993 in the constellation Hydra was identified. The Hubble constant derived from this single event was about 70 plus or minus 12. With uncertainties that large, a single event could not resolve the tension, but the central value sat between 67 and 73, tantalizingly in the middle. As more neutron star mergers and other events are detected and localized to their host galaxies, the gravitational wave estimate of the Hubble constant will become more precise. Current projections suggest that with roughly 50 well-localized events, the statistical uncertainty on the gravitational wave Hubble constant could shrink to a few percent. That would be precise enough to definitively favor one side of the tension or the other. The LIGO-Virgo-Cagra network, operating at improved sensitivity after several upgrades, is accumulating events at an increasing rate. The Einstein telescope, a proposed next-generation gravitational wave detector in Europe that would be built underground in a triangular configuration 10 kilometers on a side, is designed to detect events that are currently too distant for existing detectors. It would accumulate hundreds of thousands of events per year, allowing the Hubble constant measurement from gravitational waves to reach precision comparable to electromagnetic methods. If the gravitational wave Hubble constant converges to 73, it confirms the distance ladder and deepens the tension with Planck. If it converges to 67, it sides with the cosmic microwave background and suggests that the distance ladder has an unidentified systematic error. If it lands somewhere in between, it may be telling us something more complex about the universe's expansion history. There is also a third, largely independent method of measuring the Hubble constant that uses time delays from gravitational lensing of distant quasars. When a massive galaxy lies almost exactly between Earth and a distant quasar, the galaxy's gravity bends the quasar's light along multiple paths, producing multiple images of the same quasar in our telescopes. Because the light paths have slightly different lengths and pass through regions of slightly different gravitational potential, the light traveling each path arrives at a slightly different time. Changes in the quasar's brightness, as its central black hole flares up and dims, appear in one image before they appear in the others. Measuring those time delays gives information about the geometry and expansion rate of the universe. The H0 likelihood collaboration and its successor TD Cosmo have used this technique on a sample of strong gravitational lenses and derived a Hubble constant in the range of 73, consistent with Riess's distance ladder. Independently, other analyses of the same lensing data, using different assumptions about the mass distribution of the lensing galaxies, have found values closer to 67, illustrating how sensitive the method is to modeling assumptions. Improving the lens time delay method requires better models of the mass distribution in lensing galaxies, which in turn requires detailed spectroscopic surveys of the stellar kinematics in those galaxies. Several major spectroscopic programs are underway or plan to provide exactly that. Future improvements in lens modeling, combined with larger samples of well-measured lensing systems, should allow the time delay method to weigh in on the Hubble tension with precision comparable to the other approaches. The accumulation of these independent methods, gravitational waves, lens time delays, and the distance ladder, all triangulating on the same answer, or failing to, will be decisive over the next few years. It is worth emphasizing how unprecedented this level of scrutiny of a single number is in the history of science. The Hubble constant is arguably the most thoroughly measured cosmological parameter in history. It has been determined by dozens of independent teams using dozens of independent methods calibrated against dozens of independent physical standards. Every major space telescope and many ground-based telescopes have contributed data. Several Nobel Prize winners have dedicated significant portions of their careers to it. The underlying physics of the techniques is understood at a fundamental level and tested against first principles, predictions, and yet the tension persists. That persistence is itself information. It means the answer is not hiding in any obvious systematic error that an independent check would reveal. It is not in the Cepheid blending that Webb would have caught. It is not in a miscalibrated distance scale that Gaia will correct. It is not in a wrong assumption about supernova peak luminosity that independent distance indicators like the tip of the red giant branch would expose. All of these cross-checks have been performed. The tension has survived them all. This is the clearest signal that the answer lies in the physics, not the measurements. While the Hubble tension occupies the spotlight, a quieter revolution is happening in how we think about the structure of the universe on large scales. The universe is not distributed uniformly. If you mapped the positions of all galaxies within a few 100 million light-years, you would see something extraordinary. An intricate network of filaments and walls, dense chains of galaxies strung like beads on silk threads, surrounding enormous voids, hundreds of millions of light-years across, where almost nothing lives. This is the cosmic web, and it is one of the most visually striking features of the observable universe. The cosmic web is the gravitational legacy of the early universe's density fluctuations. Small overdensities in the early universe, regions where matter was slightly more concentrated than average, attracted more matter over time, growing under gravity while underdense regions emptied out. The initial spectrum of those fluctuations, precisely measured in the cosmic microwave background, determines the statistical properties of the cosmic web today. The standard model predicts the cosmic web in rich detail. The distribution of void sizes, the thickness of filaments, the mass function of galaxy clusters, the correlation between galaxy positions on large scales. These predictions have been tested against surveys like the Sloan Digital Sky Survey and the 2-degree field galaxy redshift survey, and they match beautifully. But as surveys get deeper and the cosmic volume they probe gets larger, subtle discrepancies are appearing in the density of the largest scale structures. One persistent observation is the existence of what astronomers call supervoids and superstructures, regions of the universe that appear significantly emptier or significantly denser than cold dark matter simulations predict on scales of hundreds of millions of light-years. The Boötes void, discovered in 1981, is a nearly spherical empty region, roughly 330 million light-years across, containing only about 60 galaxies where standard models would predict several thousand. The Sloan Great Wall, discovered in 2003, is a filamentary structure roughly 1.37 billion light-years long, larger than cold dark matter simulations typically produce. These anomalies do not decisively falsify the standard model. They might be rare but statistically allowed fluctuations within cold dark matter, but they add to a growing catalogue of things that, while individually not conclusive, collectively point in the same direction. Something about the large-scale structure of the universe is slightly different from what the simplest version of the standard model predicts. The S8 tension reinforces this picture. S8 is a combination of two cosmological parameters, sigma 8, which measures the amplitude of density fluctuations on a scale of 8 megaparsecs, and the square root of the matter density parameter, which describes how much matter exists relative to the critical density needed to make the universe geometrically flat. The combination captures how clumpy the universe is given the amount of matter it contains. Planck's cosmic microwave background measurements predict a specific value of S8. When astronomers measure S8 directly using weak gravitational lensing surveys, they consistently find a value that is lower by about 2 to 3 sigma. The universe is slightly less clumpy than Planck predicts. 2 to 3 sigma is not 5 sigma. It is suggestive rather than definitive. But the direction of the discrepancy is consistent across multiple independent lensing surveys: Chi-DS, the Kilo Degree Survey; DES, the Dark Energy Survey; HSC, the Hyper-Suprime Cam Survey. Different instruments, different sky regions, different analysis pipelines, all finding slightly less clustering than the cosmic microwave background predicts. If both the Hubble tension and the S8 tension are real, they need to be explained by the same modification to the standard model. That constraint is powerful. It rules out many simple modifications that fix one tension but break the other. The solution, if one exists, needs to simultaneously raise the expansion rate and lower the matter clustering, two effects that do not naturally come together in the simplest extensions of the standard model. This is why early dark energy is so closely examined. It raises the expansion rate, which helps with the Hubble tension, but it also tends to raise matter clustering, which makes the S8 tension worse. The ideal solution would need to decouple these two effects in a way that no current proposal has convincingly achieved. The theoretical space is enormous. Physicists have proposed modifications to gravity, to the nature of dark matter, to the properties of dark energy, to the physics of neutrinos, and to the initial conditions of the universe. Neutrinos deserve a brief discussion here because they represent a known source of uncertainty that could affect both tensions. Neutrinos are fundamental particles, produced in enormous quantities in the Big Bang and in stellar cores. 3 generations of neutrinos are known: electron neutrinos, muon neutrinos, and tau neutrinos. They interact with other matter only through the weak nuclear force and gravity, making them extraordinarily difficult to detect. Every second, roughly 65 billion solar neutrinos pass through every square centimeter of your body without interacting with a single atom. Neutrinos have mass. The discovery that neutrino flavors oscillate into each other, proven definitively in the late 1990s, requires neutrinos to have non-zero mass. But the absolute masses of the 3 neutrino types are not known from particle physics experiments, only lower limits. In cosmology, neutrino mass matters because neutrinos are everywhere and they move fast. They contribute to the total matter density of the universe, which affects both the expansion rate and the growth of structure. Heavier neutrinos slow the growth of large-scale structure by streaming out of gravitational wells before those wells can deepen, which would lower S8. Cosmological measurements provide upper limits on the sum of the 3 neutrino masses of about 0.12 electron volts, a limit already much tighter than laboratory experiments can achieve. If neutrinos are at the heavy end of what cosmology allows, they might contribute to partially explaining the S8 tension. Some analyses have found hints in this direction, but the effect is small compared to the discrepancy, and tweaking neutrino mass alone cannot fully resolve either tension. This is the current state of cosmological theory, a rich landscape of possible explanations, each plausible, none proven, all generating predictions that future surveys will test. The deep intellectual challenge is that the standard model is so successful that breaking it requires a very specific kind of new physics. You cannot simply remove dark energy and replace it with something else, because the accelerating expansion is observed directly in supernova surveys and independently confirmed in the geometry of the cosmic microwave background. You cannot simply change the nature of dark matter in a drastic way, because the cosmic microwave background's acoustic peaks are exquisitely sensitive to the dark matter density, and Planck's measurements pin it down with sub% precision. Every proposed modification has to be surgically precise, fixing what is broken without disturbing what works. This constraint is what makes the Hubble tension so theoretically interesting. A 5 sigma discrepancy that resists every mundane explanation is calling for surgery on the standard model in a specific region, and the outline of the cut is slowly becoming clearer with each new measurement. The cosmic microwave background is not finished giving up its secrets. It contains information not just in the temperature fluctuations, but in the polarization of the light. Temperature fluctuations arise from density variations in the early universe. Polarization patterns encode the effects of gravitational waves, primordial ripples in space-time produced during inflation, the hypothetical period of exponential expansion that stretched quantum fluctuations to cosmological scales in the first fractions of a second after the Big Bang. Detection of the characteristic polarization pattern, called B modes, produced by primordial gravitational waves, would be direct evidence for inflation and would constrain the energy scale at which inflation occurred. The Simons Observatory in Chile and the proposed CMB Stage 4 experiment, a network of microwave telescopes in Chile and Antarctica, are designed to search for these polarization signatures with sensitivity far beyond what Planck achieved. Inflation is the framework that explains why the cosmic microwave background looks so uniform across regions that should never have been in causal contact, why the temperature is the same to 1 part in 100,000 in all directions, even though opposite sides of the sky have been receding from each other faster than light since shortly after the Big Bang. The standard story is that a brief period of enormously rapid expansion stretched a tiny, causally connected region to cover the entire observable universe before the normal hot Big Bang expansion took over. Everything we see today was once close enough to reach thermal equilibrium. The details of inflation, including the energy scale, the field driving it, and the mechanism that ended it, all leave imprints in the cosmic microwave background that future experiments will probe. Those imprints also affect the initial conditions that seed structure formation, which connects back to both the Hubble tension and the S8 tension through the primordial power spectrum of density fluctuations. A completely different approach to the Hubble tension dispenses with modifications to the early universe entirely, and instead asks whether our measurement of the local expansion rate might be biased by our location in the cosmos. Astronomers have known for decades that we live in a region of the universe that is somewhat underdense, a large void roughly 300 million light-years across, sometimes called the KBC void after the astronomers Keenan, Barger, and Cowie, who quantified it in 2013. If we are inside an underdense bubble, the galaxies on our side of the bubble wall are falling outward toward the denser surrounding universe, which means we would observe them to be receding from us slightly faster than the average cosmic expansion rate. This effect, called cosmic variance or the local void hypothesis, could potentially explain a few percent of the Hubble tension. If the expansion rate inside our local void is genuinely a few percent higher than the cosmic average because of gravitational infall dynamics, then the measurement of 73 is not measuring the true Hubble constant of the universe. It is measuring the expansion rate in our slightly special neighborhood. The problem with this explanation is that the KBC void, while real, does not appear deep enough to account for the full tension. Studies using galaxy surveys to map the underdensity of our local region find that it would produce at most a 1 to 2% upward bias in the locally measured Hubble constant. The tension is 9%. The local void is not big enough, deep enough, or empty enough to explain the whole thing. However, some theorists have proposed that we might be inside an even larger underdensity than current surveys have mapped. Future surveys, particularly Euclid and the Vera Rubin Observatory, will map the galaxy distribution out to much larger distances and will either confirm or rule out this possibility. Another class of explanations involves modifications to gravity itself. General relativity has been tested with extraordinary precision in the solar system, in binary pulsars, and in the strong field regime of black hole and neutron star mergers through gravitational waves. It passes every test. But these tests probe gravity at relatively small scales and relatively high densities. On cosmological scales, millions and billions of light-years, general relativity has never been tested independently of the assumptions built into the standard cosmological model. If gravity deviates from general relativity on large scales, perhaps by becoming slightly stronger at large distances, or by the gravitational constant varying slowly over cosmic time, the expansion history would differ from the relativistic prediction, and both the Hubble constant and the growth of structure could be altered. Modified gravity theories come in many varieties. Some add extra scalar fields that couple to gravity at late times. Some modify the action that determines how space-time geometry evolves. Some are inspired by theories of extra dimensions, in which gravity can leak into extra spatial dimensions on large scales, appearing weaker than general relativity predicts. The challenge for modified gravity theories is the same as for all other modifications. They have to fit the cosmic microwave background, the baryon acoustic oscillations, the observed rate of gravitational lensing, and produce a Hubble constant consistent with the distance ladder. No modified gravity theory has yet been shown to pass all of these tests simultaneously while also resolving the Hubble tension. But the field is active and the tests are tightening with every new survey. One of the most important upcoming tests will come from measuring the growth rate of cosmic structure independently of the expansion rate. The growth rate tells you how fast matter is clumping together under gravity over cosmic time. In general relativity, the growth rate and the expansion rate are related in a specific way determined by the theory. If gravity is modified, that relationship changes. The dark energy spectroscopic instrument, currently mapping tens of millions of galaxies, will measure the growth rate of structure through a technique called redshift space distortions. When galaxies fall toward overdense regions under gravity, they have a peculiar velocity component on top of the cosmic expansion. This peculiar velocity shows up as a distortion in the apparent clustering of galaxies measured in redshift space. The amplitude of that distortion is directly related to the growth rate. If the growth rate measured by this instrument is consistent with general relativity's prediction, given the expansion rate measured by the distance ladder, then modified gravity is disfavored. If there is a discrepancy, modified gravity gains traction. It is worth pausing on the Cepheid variables themselves because the physics of these stars is extraordinary and often skipped over. A Cepheid variable is a giant star, typically 10 to 50 times the mass of the Sun and several thousand to 100,000 times more luminous. What makes Cepheids special is a pulsation instability driven by a mechanism called the Kappa mechanism. At specific temperatures in the outer layers of the star, singly ionized helium exists in a state that becomes more opaque to radiation as it is compressed, rather than less opaque as most gas does. When the star's outer layers contract under gravity, this helium layer traps the escaping radiation, which builds up pressure and pushes the layers back outward. As the layers expand, the helium ionizes more completely, becomes transparent again, and the pressure drops, allowing the layers to fall back inward. The cycle repeats, producing a regular pulsation with a period that depends on the star's mean density and therefore on its luminosity. The Type 1, a supernovae that the distance ladder relies on at its outermost rungs, have a similarly fascinating physical story. A Type 1a supernova occurs when a white dwarf, the dense remnant of a dead star roughly the size of Earth but with the mass of the Sun, accumulates enough material from a companion to approach the Chandrasekhar limit. The Chandrasekhar limit is about 1.4 solar masses, the maximum mass that can be supported by the quantum mechanical pressure of electrons. As the white dwarf approaches this limit, the pressure fails and the star detonates in a runaway thermonuclear explosion that destroys it completely. Because the trigger mass is always approximately the same, the amount of material detonating is always approximately the same, and the peak luminosity of the explosion is approximately standard. In practice, there are small variations. The color and decline rate of a supernova's light curve correlate with its peak luminosity in a way that allows the intrinsic brightness to be calibrated from the observed light curve shape. This standardization procedure, developed primarily by Mark Phillips in 1993, transformed Type 1a supernovae from interesting objects into the standard candles that enabled the discovery of dark energy. The standardization is not perfect. Supernovae in different environments, different host galaxy types, different stellar populations show systematic differences in their calibrated luminosities at the level of a few percent. Understanding and correcting for these environmental dependencies is an ongoing source of work in supernova cosmology. Recent analyses have found suggestions that supernovae in older, more passive galaxies behave slightly differently from those in younger star-forming galaxies. Some studies find that applying a correction for this host galaxy dependence shifts the derived Hubble constant slightly downward, though not enough to fully close the gap with Planck. The effect is real but small, and it is now being incorporated into standard analyses. All of these details, the metallicity correction for Cepheids, the environmental correction for supernovae, the lens model, uncertainties for time delay cosmography, exist because cosmology is a science of precision, where every fraction of a percent matters and every source of bias has to be identified and controlled. The fact that the Hubble tension survives all of these corrections and cross-checks, that it does not dissolve when one systematic concern after another is addressed, is the single strongest argument that it is not a measurement artifact, it is a real discrepancy in the physics. If you find yourself genuinely curious about how the universe is built and how scientists are working out what it has been hiding, take a moment to like and subscribe so more questions like these can find their way to you. There is still a great deal worth understanding. It is worth tracing the relationship between the Hubble tension and the history of the universe's expansion in more detail, because the expansion did not proceed at a constant rate, and the rate at which it changed contains information that neither side of the dispute fully explains. In the very earliest moments after the Big Bang, the universe was dominated by radiation. Photons and other relativistic particles filled space at unimaginable density and temperature. The expansion rate in this radiation-dominated era followed a specific mathematical relationship. The universe expanded proportionally to the square root of time. As the universe cooled and matter became the dominant component, the expansion shifted to a different relationship, proportional to time to the 2/3 power. Then, a few billion years ago, dark energy, with its constant density even as the universe expanded, began to dominate over the diluting matter density, and the expansion shifted again to an exponential acceleration. Each of these transitions leaves signatures in the distribution of galaxies and in the cosmic microwave background that cosmologists use to reconstruct the expansion history. The extraordinary thing is that a single value of the cosmological constant lambda fits all of these signatures simultaneously. The same number that describes the current rate of acceleration also correctly predicts the transition point where dark energy took over from matter, roughly 7 billion years ago. The same number that fits the cosmic microwave background geometry also predicts the abundance of massive galaxy clusters in the nearby universe. This internal consistency is what makes the standard model so compelling, and why the Hubble tension is so disturbing. The tension does not just mean the expansion rate is wrong, it means the entire expansion history, as seen from its present endpoint, is wrong in a way that requires the rest of the model to be adjusted to compensate. To close, it is worth thinking about what the discovery of new cosmological physics would mean, not just scientifically, but in a larger sense. Every generation of astronomers has believed in some corner of their minds that they were the ones who finally had it figured out. The ancient Greeks believed the stars were fixed to crystalline spheres. Medieval astronomers added epicycles and more spheres to explain the wandering of the planets. Newton believed the universe was a clockwork mechanism running by mathematical rules that were complete and final. Physicists at the end of the 19th century famously believed that the era of fundamental discovery was drawing to a close. Each generation was wrong in almost exactly the same way. They had discovered laws that worked beautifully within their observational reach, and they had mistaken the boundaries of their reach for the boundaries of reality. We are not exempt from this mistake. The standard model of cosmology is the most successful framework ever built for understanding the large-scale universe. It is almost certainly not the final one. What we know today is deeper, more precisely measured, and more internally consistent than any previous cosmological framework. The Big Bang is not in question. The expansion of the universe is not in question. Dark matter is not in question. Dark energy is not in question. These are structural features of the universe confirmed by multiple independent lines of evidence and embedded deeply in any framework that succeeds the standard model. What is in question is the specific mathematical model we use to describe these features, the specific properties we assign to dark energy and dark matter, the specific sequence of events between the Big Bang and now. The next framework will contain the current one as an approximation, in the same way general relativity contains Newtonian gravity as a limiting case. It will reduce to lambda CDM in the regimes where lambda CDM works perfectly, and diverge from it in the regimes where the current tensions arise. That is how science works. Not by abandoning what works, but by finding the deeper principle that explains both what works and what does not. The universe that contains a Hubble tension and overabundant early galaxies and prolate galaxy shapes and slightly less clustering than expected is a more interesting universe than the one that matched our model perfectly. It is a universe that has something left to teach us. It is a universe that is not finished revealing itself. The James Webb Space Telescope will be observing for another decade and a half or more. Euclid has begun its survey. The Roman Space Telescope will launch within a few years. Gaia will complete its Cepheid catalogue. The Dark Energy Spectroscopic Instrument will finish mapping tens of millions of galaxies. The Vera Rubin Observatory will observe billions of galaxies and tens of thousands of supernovae. The gravitational wave detectors will accumulate neutron star mergers. All of this data is coming. The scientists analyzing it will be doing what scientists have always done when a stubborn discrepancy refuses to go away. They will keep measuring, keep checking, keep building theories, keep falsifying the wrong ones, and eventually they will find the thing that makes everything make sense. The universe is out there expanding at whatever rate it expands at, governed by physics that does not care whether our models match. Our models will catch up to it. They always have. What is happening right now in cosmology, this accumulation of precise tensions from multiple independent directions, is not a crisis of confidence. It is the sound of a science operating at the frontier of knowledge, pressing against the boundary of what it understands, finding that boundary closer than expected, and pressing harder. That is exactly where science should be. That is exactly what science is for. Perhaps the most honest thing that can be said about where cosmology stands today is this: we have measured the universe well enough to find where our understanding of it breaks down. That is an achievement, not a failure. Most of human history has been spent without the tools to see far enough or precisely enough to locate that boundary at all. For most of recorded history, the universe was everything within walking distance, then sailing distance, then everything visible to the naked eye, which for the clearest-eyed observers under the darkest skies amounted to a few thousand individual stars and a handful of fuzzy patches that would later prove to be other galaxies entirely. The universe as a measurable object with an age and an expansion rate and a composition is less than 100 years old as a concept. The idea that the cosmos began, that it has a history, that we can trace that history backward through the light arriving at our telescopes from billions of years ago, is extraordinarily new in the span of human thought. In that context, the Hubble tension is not a sign that cosmology is failing. It is a sign that cosmology has grown precise enough to ask questions that go beyond its current answers. That is exactly the state a science should aspire to. The answer is coming, not because of optimism, but because the instruments exist, the techniques are proven, and the data is accumulating. The universe has been patient with our measurements for nearly 14 billion years. It will be patient a little longer while we figure out what it has been trying to tell us. Scientists still do not know what is causing the Hubble tension. They do not know whether early dark energy is real or merely a mathematical convenience. They do not know whether dark matter is cold, warm, or something else entirely. They do not know why the early universe produced galaxies that appear more massive and more structured than the models allow. They do not know what dark energy fundamentally is, even after 25 years of treating it as a cosmological constant in the equations. These are not admissions of failure. They are the live questions at the edge of what we know, the frontier where telescopes are pointing, theorists are working, and data is still coming in. The data that will resolve these questions is not hypothetical. It exists right now, encoded in the photons striking Webb's detectors in the cold dark beyond Earth's orbit, in the electromagnetic signatures of gravitational wave events reaching LIGO's mirrors across 4 kilometers of laser-maintained vacuum, in the spectral signatures of billions of galaxies being catalogued by the Dark Energy Spectroscopic Instrument, in the positions of nearly 2 billion stars being tracked by Gaia to micro-arcsecond precision. It is being gathered, stored, processed, and analyzed by thousands of scientists on every continent. The answer is in there. Someone will find it. The only question is, which dataset, which analysis, which moment of recognition will be the one that makes the pieces click into place? When that moment arrives, it will not feel like an ending. It will feel like a beginning. Every great resolution in the history of physics has opened more questions than it closed. The discovery that matter is made of atoms led immediately to the question of what atoms are made of. The answer, electrons and nuclei, led to the question of what nuclei are made of. The answer, protons and neutrons, led to quarks, and quarks led to quantum chromodynamics, which is still being worked out today. Each answer is a door into a larger room. Whatever resolves the Hubble tension will open a room we have not seen yet. The universe has never revealed itself to be smaller or simpler than we imagined. It has only ever revealed itself to be larger, stranger, and more deeply structured than anything we expected. That pattern, the pattern of science itself, gives no indication of stopping. We are ready for the next room.